Chemsters, this is Mrs. Vandeloy bringing you some more Chemster video. I'm sorry I can't be here today. Hopefully I'll be here tomorrow. And we're going to still go on and talk about the next section in our notes. Now, I hope that you've already gone over your homework from section 9.3 where you were converting grams or liters or molecules, something into moles to fill out your BCA table, and then figuring how much grams or liters or molecules you have when you're done. So again, the BCA table has only moles. Now if we go back and look at what we did on Friday, here we actually weighed out, this is our notes from Friday, 1.4 grams of copper. So then we figured out, oh, we had 0.022 moles of copper. And then what else did we assume? We assumed we had excess of silver nitrate. What did we make? Well, if we go down here, we end up making 4.7 grams, yes I know, periodic table, of silver. And this is how much money I was going to get, $2.50. I might be able to buy a Big Mac with that. So I don't think I'm going to retire anytime soon. Don't worry. It's not why I'm not here. So anyway, so we made 4.7 grams. So this next section, 9.3, we're going to talk about how much I should have made, and we're also going to talk about this idea of, well, what if I don't have excess? What if I have an exact amount of both quantities? What do I do with that? So that's what your limiting reactant is going to be about, when which one will run out first, and you're going to figure that out, and your percent yield. So let's start off with percent yield. That's kind of the easier part. It's a formula. I can compute theoretical yield, actual yield, and percent yield. But I guess before we begin, make sure you have a calculator. If you need to, go grab one, make sure you turn it. Make sure you have a periodic table, and if I were you, I would have a pencil with an eraser. Okay, so if you need to pause this and grab your supplies, then go ahead and do that. Okie dokes. So what is percent yield? Percent yield is actual from lab. Hey, we're going to be in lab soon, and we are going to make some product. We're not going to be making silver, so no, you can't retire early, all right? But we're going to make a product. We're going to make a solid, and so we're going to weigh it when it's all over, said and done, and that is what you will actually make. That is your numerator that goes on top. Your theoretical is what do you get from stoichiometry. So like from the example before, I should have made 4.7 grams of copper using my BCA table. Now I'm sorry, 4.7 grams of silver. Did I actually make 4.7 grams of silver? I don't know. I haven't weighed it. All right, but that is how much I should have made. So that's my theoretical, and then times 100%. So if you had if you only made 1 gram of silver, that'd be really sad. That'd be only 50 cents. But if you actually made 1.0 grams of silver in the above example, what's my percent yield? So take my 1 gram, that's what I actually got. I will give you that. That's typically going to be in your problem. Divided by what you should have. That's what you're probably going to calculate using your BCA table as your theoretical. That's what you will calculate. And then you're going to multiply by 100%. And when you do that, go ahead and calculate that. I sure hope you got something along this line here, but what's wrong with that number? It's your sig figs. Here, this is probably where you need to get your sig figs from. Also, the sig figs from your BCA ended up being 2 sig figs. I made it easy on you. So I should just have 2 sig figs here. And there we go. So what do you think? I have a pretty low percent yield, don't I? So if your percent yield is less than 100%, yes it is, it's 22%, then you lost some product in the process. Well, that's a bummer. Okay, because if I lost a product, I didn't make nearly as much money as I wanted to, did I? If my percent yield is greater than 100%, you do not have pure product. There must be something else in there to cause your mass to be too big. Okay, so it'd be an impure substance. So anyway, that is percent yield, and we'll come back to that, don't worry. So objective now, we're going to identify limiting reagents or reactants, and using this information to solve stoichiometry. So limiting in excess. Use the following procedure when you're given quantities of all reactants. What's different from the last week's work is that you were given 1 reactant's quantity and not the other. So what do you do if you're given quantities of both reactants? If you need to make some kind of note, star that, circle that will be the difference. That's when you know you're going to have to use limiting reactants. So what is a limiting reactant? It's a reactant that is used up first. Oh, folks, this word right here, and, is so important. All right, and determines the amount of product. That's an important word. Okay, I'll show you why in a second. Your excess reactant, remember what we talked about? That is excess. Remember that? Is a reactant which is left over. Now I'm not going to tell you which one's left over. You're going to tell me which one's left over. So let's go back to my brownie mix. Okay, so if I open up my cabinets and I actually have 3 brownie mixes, an unlimited amount, I'll just kind of do that right here. 4 cups of, 4 cups of, it should be oil. Make that oil. So 4 cups of oil and 6 eggs. Which one is going to run out first? Okay, so what am I going to do? Can you tell just looking at this? I can make 3 brownie mixes from here. I can make 8 batches because I have 4 cups of oil. But how many eggs do I have? I only have 6 eggs. So I only think I can make 2 batches of brownies there. So I think my limiting reactant is going to be eggs. Okay, so it's going to be my eggs. And which ones are in excess? It's the other ones, the brownie mix. All right, my water and my oil are all in excess. So how many brownies can I make? I can make 2 batches, which would be 32. So watch what happens. I want to show you something. So I'm going to bring down my limiting reactant, my 6. And what do I do when I bring it down? I divide it and multiply. Divide by what you have, multiply by what you want. Watch what happens. So what's 6 divided by 3? 2. Okay, so it's 2 times 1. 2. I still have a positive number of brownie mixes left over. I'm going to use 2 brownie mixes. All right, what's 6 divided by 3? 2. What's 2 times 1.5? 3. Well, what's excess minus 3? Excess. I have plenty. I have a whole faucet full, if you will. All right, what's 6 divided by 3? 2. What's 2 times 0.5? 1. And I still have a positive 3 left over. And let's do one more time. What's 6 divided by 3? 2. 2 times 16 is 32. So I'm going to make 32. There we go. So what do you notice about your limiting reactant? Your limiting reactant is the one that has a 0 when you subtract out. How do you know you picked the right one? The rest, the excess, are all positive numbers. That's how you know you chose the right one. So if I picked, let's say, oil. So if I have 4 divided by 0.5, that's 8. And so 8 times 3 is 24. If I put a 24 here, what's 6 minus 24? It's a negative 18, isn't it? You chose poorly. I'll probably show you a clip from Indiana Jones soon when I get back, and I'll show you the famous scene where the guy chose poorly, right? So if you get a negative number, I should say 24, right? If you get a negative number and you subtract out, you chose the wrong one to be a limiting reactant, okay? So make some kind of note with that. So if you do it right, your limiting reactant is 0. Your other reactant or reactants are going to be positive, and it is this number that determines your product. Okay, so let's see how this actually works. Okay, let's turn the page. Okay. All right, so here we go. If you have 5 atoms of carbon and 6 molecules of hydrogen, notice that's what I have. What's the limiting reactant? Well, what do I have to do first, everyone? Of course, I need to balance. I'm going to put a 2 here. All right, so if I have 5 carbons and 6 molecules, what's going to run out first? Well, let's see how this works. This is a visual of what's going on. So for every 1 atom of carbon, I'm going to use 2 molecules of hydrogen, right? So for every 1, I'm going to use 2. For every 1, I'm going to use 2. For every 1, I'm going to use 2. Can I keep going at this point? And the answer is no, I can't. Why not? Because I ran out of the H2s. So which one is limiting? H2, they're all gone. I have 0 of these. Which one is excess? Carbon, because I have 2 leftovers. So that means how many CH4 methanes can I use? Well, let's see here. I'm going to make 3 of those, aren't I? If you look, I'm going to make 3. And does that make sense? Well, let's find out. Let's do the same thing, but we're going to put 5 here and a 6 here. This is where you might want to use a pencil or just pause, or not pause, but just listen and watch me, because I'm going to make a mistake first, okay? I'm going to just pick one. Well, hey, 5 is the smaller number. I'm going to pick 5 to be my limiting reactant. Okay, well, try it. So again, I'm going to, put a 5 here. What's 5 divided by 1? Well, 5. 5 times 2 is 10. So what happens when I subtract? I get a 0. Good. But what's 6 minus 10? -4. Wrong. Can't do that. We can't have a -4 leftovers. So I chose poorly. So let's try that one again. So if I have 5, oops, come back here. If I have 5 and 6, I'm going to pick the other one. It's not a big problem if you chose poorly the first time. Pick right the next time. So I'm going to put a 6 here. So what's 6 divided by 2? 3. 3 times 1 is 3. So what do I get here? I get a 0 and a +2. Oh, I chose wisely. Yes, I sure did. So now I can go ahead and figure out how much product I make. That's a 0, by the way. It's a 0. What is 6 divided by 2? It was 3. And so I'm going to add 3. And how much product did I get? I made 3. It's a +3. I made 3 CH4s. So that's how this whole thing works out. So I have leftover carbons, used up all my hydrogens, and my hydrogen is what determined how much product, that I couldn't keep going anymore. So once I run out, I can't make any more product. So let's see what I'm doing down here. Well, it looks like it's pretty similar. So why don't you pause this, balance it, cross things out? Why don't you determine what you have? So pause this and then we'll see how we do. Okie doke. So what's the first thing we need to do is we need to balance this. I'll put a 2 here and a 4 here. So what does that tell me? For every 4 sodiums, I need 1 O2. So 1, 2, 3, 4, I need 1 O2. 1, 2, 3, 4, I need 1 O2. Well, can I keep going? No, I can't. I can only do this twice, so I can only make 2 products. And I do have leftover oxygens. So let's see how this works using the BCA table. So I have 8 here and 3 here. Now, notice that the 8 is actually the bigger number this time. All right, so let's go ahead and use 8, because I already know that it's going to work. So here is 8. What's 8 divided by 4? 2. 2 times 1 is 2. Now let's check our work. I get a 0 and I get a +1. I did it right. I chose wisely. So now go back and use the same 8 again, because that will determine my product. 8 divided by 4 is 2. 2 times 2 is 4 products. All right, and I do that right? I think so. And so then I get a 4 here. Okay, and so that's what I get. Hopefully that worked out for you. Let's go ahead and do it using what we learned before, okay? So to determine limiting reactant in a chemical reaction, look at the definition again, choose the first reactant, see if it works. If not, choose the second. Use your pencil, you might have to erase. So go ahead and again, pause this and see how you do. See if you can't figure out which the limiting reactant is and how much product you make. Okie dokes, let's see how we do. We got a 2 here and a 3 here and a 0 here, of course. So let's use the first one. What's 2 divided by 1 is 2. 2 times 3 is 6. So I get a 0 and a row, a -3. I can't do that, can I? So I chose poorly, so I need to do this again. So if 2 didn't work, now what? Well, then the 3 must be my limiting reactant, mustn't it be? So I'll put a 3 here. What's 3 divided by 3? 1. 1 times 2 is, 1 times 1 is 1, so this is a 1. So subtract, I get a 0 and a +1. I chose wisely. So now I need to use this 3 again. 3 divided by 3 is 1 times 2 is 2, so I get a plus 2 products. So my limiting reactant is my hydrogen gas. Okay, how much ammonia do I make? I make 2 moles of ammonia. Hey, here's another question I could ask you. How many moles of N2 are left over? I get 1 mole left over. There's a bunch of questions we can ask. All right, how about the next one? Uh-oh, I did not balance this one for you. So you need to balance it first and then go ahead and try this, okay? So pause this and work this out. Okie dokes. Well, I think you probably run into a little bit of an issue balancing this, but if you put a 2 here, I think all your issues will be solved. So if I have a 2 times 2, I have 4 carbons, there we go. I have 12, so I'll put a 6 here. And now what? 4 times 2 is 8, plus 6 is 14, so I have a 7 right here. So let me kind of clean up a little bit here, because I may need that room. All right, so now let's read the problem. What if I have 7 here, and I have 10 here? That's a 10, by the way. What's my limiting reactant? How many moles of carbon dioxide and water can be made? So I'll just use my first one, 7. So what's 7 divided by 2? That's 3.5. I told you you're going to need a calculator, all right? So let me get out my calculator. What's 5 times 7? That's 24.5. Can you see we have a problem right now? I'm not even going to put it down because I'm going to have to erase it. If I put a 24.5 right here, then I know I'm going to have a negative number. So I chose poorly. So I'm not going to use 7 as my limiting reactant. I'm going to use 10. So 10 divided by 7 is 1.4285, yada, yada, yada. And multiply that by 2. And now I get 2. I should probably use more than, I hate these sig fig things. So 2.9, so it'd be a 3.0. So this is a 3 using 1 sig fig, which is a pain in the neck. Oops, sorry, that's a 10. So this is a 0. This is using 1 sig fig, so that's a 4. Why 1 sig fig? Because that's how many of these guys have here. And so now what? I am going to use my 10 as my limiting reactant. So again, 10 divided by 7, all right, is that 1.4 number, and then I'm going to multiply that by 4, and I got 5.71, so 1 sig fig is going to give me a 6. And then I'm going to do it again, 10 divided by 7 times 6, and that's 8.57, so that's barely a 9. So using 1 sig fig, let's answer the questions. Which is my limiting reactant? My O2 is my limiting reactant. And it doesn't make a difference which one shows up first. It all depends on how much you actually have. That's what's going to determine your limiting reactant, not because it seems to be always the second one. How many moles of the oxygen and, the carbon dioxide and water can be made? Well, we have 6 moles of carbon dioxide and 9 moles of water, again using sig figs. Oh, by the way, hey, what kind of reaction is this? Hopefully you remember it is a combustion. Hey, what was the one above? What does that one look like? Do you remember what 2 becomes 1 is? Synthesis. That was correct. All right, let's see about the next one. All right, here we have 1.75 moles of phosphoric acid. I even gave you that. How nice was I? Reacts with 5.00 moles of sodium hydroxide. Uh-oh, you need to write out the balance equation. So again, pause this and write it out. I didn't give you the products, did I? You need to go back and think what kind of reaction it's going to be and then determine your product. So pause this and let's see how you did. All right, well, hopefully you got something along that line. Hey, I gave you the phosphoric acid and sodium hydroxide, +1, -1, right? What kind of reactions? I have 2 ionics pretty much, all right? So the phosphoric acid is ionic. We'll talk about that in 2 more chapters and why that is ionic, even though H is a nonmetal. So what kind of reaction would be ionic and ionic? Hopefully you came up with double replacement. Very good. So if you have a double replacement, what do you have to think about? You have to think about your outers and your inners, don't you? Do you remember doing that? So what are my outers? I get H OH. Don't worry about the 3. We're going to come back to that. We just get HOH. And what does that actually make? Come on, you know what that is. That is water. Very good. And then what? My inners is Na and PO4. Well, the metal always has to be written first, okay? So don't put PO4 Na, that'd be wrong. Now you have to consider your charges. What's the charge of sodium? +1. What's your charge of phosphate? -3. Oh, you had to memorize that. So then what? You have to crisscross, and you end up with Na3PO4. Folks, if you mess up there, oh, you're going to have a hard time doing the problem right, won't you? Okay, so you have to know how to do that. So now I have to balance. And if you've already gotten this far, then hopefully you've already figured out how to balance it. Let me use red. Red looks good. So I'll put a 3. Oops, that's a blue, isn't it? And a 3 here. Okay, and there it is balanced. So hopefully you agree with me. So what is the first thing I have to do? Well, I think the first thing I have to do is, oh, I got some moles. I don't have to convert anything. Oh, hallelujah. So 1.75 and 5.00. So if I choose, oh, what a horrible English. If I had chosen the first one, all right, 1.75. What's 1.75 divided by 1 times 3? I'll do that. 1.75 divided by 3. I'm sorry, silly Mrs. Vandoy, times 3. 1.75 times 3. What do I get? Let's see here. I got 5.25. Can't do that, can I? I can't do that. I'm going to get a negative number. So that is not my limiting reactant. So the 5 is my limiting reactant. So let's try this again. So I'll start over here, and I'll have 5.00. What's 5.00 divided by 3? I think it's like 1 point something, right? 5.0 divided by 3, 1.66666. All right, times 1 is 1.66666. And I think if I do my math right, I think I can do that. And it works out. Hallelujah. I get a positive and I get a 0. So which is my limiting reactant? Sodium hydroxide. Which is my excess? Phosphoric acid. All right. So now I can finish off these guys, can't I? So that 1.66666 times 3 is 5. And 1.66666 times 1, that's my 1, that's not a 0 or a 6, that's a 1, I was just showing you where I was getting that from, is 1.67, so I have 5 moles of water and 1.67 moles of sodium phosphate. Now, what is my next question asking me? How many, not moles, how many grams, periodic table, of each product are made? That's right. So we need to factor label. So why don't you go ahead and finish that, and then you can see how I did. All right, let's go ahead and do our water first. So how many grams of water are there in 5 moles? Well, what unit has to go on the bottom? Moles. What unit has to go on the top? Grams. Periodic table. So H2O, I hope you still remember, is 18.02. And when you multiply these out, you get exactly 90.1. And what's so exciting about that? That's the right number of sig figs. All right, so what about the next one? Sodium phosphate. You have 1.67 moles of sodium phosphate. What unit must go on the bottom? Moles. What unit goes on top? Periodic table, oh, grams, periodic table, and I'm getting a lot of chocolate over here, I don't know about you. And I'm hoping this is what you got for the molar mass of sodium phosphate, 3 sodiums, 1 phosphorus, and 4 oxygens. And when I get done here, I get that many. Well, Mrs. Vanderlooy, that's too many sig figs. I know, I need 3 sig figs here, so I need 3 sig figs here, so that's equal to that. Hopefully this is all starting to make sense. Do you see now why this is a accumulation of the last, 4 chapters pretty much? Because what did you have to do up here? You had to figure out the formulas, didn't you? That was from the early part of chapter 7. Then what? Chapter 8, we had to balance this. So chapter 7.3, we had to do the math to go from moles to grams and that kind of stuff. And then chapter 9, we're putting this whole thing together and filling out the BCA table. So if you are still struggling with nomenclature, nomenclature, well, I'd keep looking that over if I were you. If you couldn't remember that phosphate was a -3 and hydroxide is -1, you might want to keep reviewing that. Otherwise, your test is going not to go well for you. All right. I think we have one more problem to do, so let's see what the next page brings. All right, so now we have 50 grams of copper reacts with 100 grams of silver nitrate. This should look really familiar. This is what we did on Friday. What is our reaction? So we have copper and silver nitrate. Hey, what's the formula for silver nitrate? What's the charge of silver? What's the charge of nitrate? What's the formula for silver nitrate? That's what I got. And what am I going to make? What kind of reaction is this? Let's think about it. I have an element and an ionic. What kind of reaction is that? That is single replacement. So now what? What am I going to do? I'm going to swap places. So nitrate now gets the copper. And what's left to do at this point is balance it. Yeah, we need to balance it. So let's see here. I should put a 2 here and a 2 here. That's right. So now what? Let's go. I have 50 grams. Oh no, it's grams, not moles. Periodic table. So I have to now convert grams to moles so I can fill out the BCA table. So why don't you pause this and see how you're doing that. Hope you did it. So here's copper, and I need to know how many moles of that I have. Well, I looked on the periodic table, and I found 63.55, so I divided that, divide that out, I got 0.79 moles. I had to do the same thing for silver nitrate, didn't I? I found the formula mass, or the molar mass of silver nitrate. And that's how many moles I got. So what am I going to do with this now? I'm going to put those two numbers in my BCA table. All right, so here I have 0.79. Oh, I got red again. And 0.589. 0 and 0. So which one do you want to pick? Well, I'm going to put 0.79 in. Well, what's 0.79 divided by 1 times 2? It's bigger than 1, isn't it? Uh-oh, I have a problem. It is not 0.79, it's 0.589. So what is, I'm getting out my calculator, what is 0.589 divided by 2, I have no idea, here we go, is 0.2945. Let's just make that 0.295, and then when I subtract, how do I subtract with those not the same number of sig figs? I have to go to the least significant place, which would be the hundreds, not the thousands. So 0.79 minus 0.295 looks like 0.50. All right, did I choose wisely? The answer is yes, I have a positive number. So my silver nitrate is actually my limiting reactant, not the one before. Remember how on Friday we said silver nitrate is in excess? No. Now it's my limiting reactant. I've left over copper. So how does this work here? So I have, if I have a 2 in front of here, this is 0.589. And it's an 8, by the way. And this is 0.295. So 0.589 moles of silver is made and 0.295 moles of copper nitrate are made. So now what? What's my next? Whoops, come back here. There we go. What is my next question? How many grams of each product are made? Not moles, grams. Go ahead and do this. Pause it. Work on it. All right, here is your moles of silver, or excuse me, your grams of silver. I got 63.5 grams of silver, and I ended up with 55.3 grams of silver nitrate. I want to do one more thing. We haven't asked this yet. How many grams of copper do I have left over? How are you going to answer that question? Listen to the question again. How many grams, periodic table, of copper are left over? Well, where do we start with that? Well, we need to start with this. How many moles of copper are left over? And then you can figure out how many grams, periodic table, of copper are left over. So go ahead and do that too. Well, is that what you got? So why only 2 sig figs? Did Mrs. Vanderlei make a mistake? No, because how many sig figs did we have when we subtracted 2 sig figs? So I needed 2 sig figs here. So anyway, percent yield, we already talked about this. I don't know why I put it in here twice, but just in case you don't know, why would percent yield be greater than 100%? Impurities, 2-8, you need to draw your precipitate. And then causes of less than, you spilled some, lost some in filtering. That would be bad. So we'll see what your percent yield will be in the lab tomorrow. All right, we got some more. So if 75 grams of siderite ore is heated with 65.8 grams of copper, 45.0 grams of iron 2 oxide, or excuse me, iron 3 oxide are produced. Determine the percent yield of iron 3 oxide. I almost said that again. Well, we have to go through the same process again. All right, and so what we're going to have to do is go from grams to moles. Oh, balance it first. And then go through the BCA. Figure out how many grams of iron 3 oxide we should make, and then find the percent yield. So let's go ahead and do that. So the first thing is, let's balance it. Go ahead and do that. So what I did is I looked at my iron. I have 2 moles of iron here, so I need to put a 2 here. That gave me 2 moles of carbon, so I had to put a 2 here. Then I had to add up all my oxygens. I have 7 oxygens on the right-hand side and 8 oxygens on my left-hand side. So I actually multiplied the oxygen by 1/2. Now, as you know, can I do that? No, Mrs. Vanderlei. So what should I do next? Multiply everything by 2. So it should be a 4, a 1, a 2, and a 4. Does that work for you? Let's check it. 4 irons, 4 irons, 4 carbons, 4 carbons, and now I have 2 times 3 is 12. I'm sorry, 2 times 3 is 6, plus 8 is 14. Here I have 12 and 2 make 14. So it's 4, 1, 2, 4. So now what do we have to do? We now have to figure out how many moles of everything we have. Why don't you go ahead and do that? Figure out moles of siderite and figure out moles of oxygen. So go ahead and do that for me. So these are the 2 numbers I came up with, and hopefully you came up with them as well. I didn't show all my work. I figured you should. And I got 0.647 moles of siderite and 2.06 moles of oxygen. I'm hoping that you can see pretty clearly which one is my liminting reactant. It's 0.647. And I get a 0 here, and 2.06 minus 0.647 is 1.413. So we chose well, all right, we chose correctly. And holy cow, I didn't do that right. Pause. All right, Mrs. Vanderlei, she forgot to divide by 4, so this is 0.162 is what it looks like. So 2.06 minus 0.162 is 1.898, so 90. All right, so hey, I found the right liminting reactant. Good. So now what? We need to determine our moles of my product. I get 0.647 of CO2. How do I know that? Well, their coefficients are the same. So 0.647 divided by 4 times 2 is 0.324. Oh, already got that. 0.647. There we go. Okay, so now what? Which is my liminting reactant? Siderite, FeCO3, which is excess oxygen. How many moles of excess are there? 1.90. How many grams of excess are there? I have to figure this out. So how many grams of O2 do I have? I have 1.90 moles times 1 mole on the bottom 32. I love my handwriting when I do it like this. All right, and that's equal to what? 1.90 times 32, and I get 60.8 grams of O2. And now it says determine the percent yield. Well, what do I need to do to determine my percent yield? I need to go back, and what do I know? I have 45 grams periodic table of iron 3 oxide. So I have 0.324 moles of iron 3 oxide. So what is my, how much should I get? So question mark grams of Fe2O3 is equal to 0.324 moles times 1 mole and 159.7 grams. Where did I get that from, everyone? Periodic table times 0.342, and that's, or 324, I'm sorry. It is 324, isn't it? Or is it 342? What did I do? I did it right. Okay. And that is 51 point, looks like 7 grams. That's a 7. So that's not my percent yield, folks. So what do I need to do? Percent yield, I'm running out of room here, I wrote too big, is the how much should I actually make? 45 grams. Let me do it over here then. So 45 grams, that's my actual. My theoretical is what I should have, and that's my 51.7 grams. So 45 divided by 51.7, and that's times 100%, of course. And I got 87.0% yield. That's not too bad. All right, I made quite a bit of iron 3 oxide. So I think I'm pretty much done here. We still have one more problem. I think your homework tonight will be sufficient. So why don't we just quit here and you start your homework. So check Google Classroom one more time. All right, that's it. Signing off. Don't wait to be great. Bye.